Hi, my name is Tom Park. I'm Director of Software Solutions at Berry Consultants. In this video, I'm going to demonstrate our FACS software simulating the design for a basket trial. And I'm going to show how we can explore design options that can allow us to optimize this kind of trial. I hope, through this demonstration, to show you firstly, what it's like to use our FACS simulation software. Secondly, how one can use simulations to make informed trial design choices. And lastly, to show you some of the trial design features that we use to make basket trials more efficient. What I mean when I say basket trial is a clinical trial where we test an experimental treatment, usually comparing it to a control arm, in a patient population where we have a number of predefined patient subgroups. These subgroups may be defined by genetic biomarkers or other patient baseline covariates, such as age or disease severity, where there is a possibility that the treatment effect is different in the different subgroups. Let's take a look at our example. So our example is that we've got a new compound for some sort of symptomatic treatment of a condition, and the endpoint is going to be mean change from baseline in some score after 26 weeks. In our patient population, we've got one principal subgroup, which is about 60% of the overall population, and four smaller subgroups that are about 10% each. And what we want to do in this example is make the following decisions at the end of the trial. If the across groups has got sufficient probability of success in a subsequent phase 3 trial, then we proceed to that phase 3 in the whole population. Otherwise, if a phase 3 based on just the principal group has got sufficient probability of success, then we proceed to phase 3 just use in that principal group plus any of the small groups that have also looked successful. Otherwise, we're going to give up development of the treatment. In other words, even if some of the small groups look successful on their own, if we haven't got success in the principal group, we're not going to be interested in going forward. And we're going to look at this design in 3 stages. First of all, we'll consider just a straightforward fixed design where we simulate the data and we do an analysis at the end. Then we'll look at adding interims in the trial and adding some futility stopping rules. And then finally, we'll try to improve how we perform with our futility stopping by adding a longitudinal model. So a little more details about this endpoint. We've got an expected standard deviation of 2 points on the endpoint, and the size of improvement we're looking for in the treatment is 1 point. And if we did a standard sample size calculation for a 2-arm trial with a standard deviation of 2 and a treatment improvement of 1 point, looking at type 1 error, two-sided of 0.05, then and power of 0.8, we would be told we needed a trial of 64 subjects per arm, 64 on control, 64 on the treatment. Now, our situation is a little more complicated than that, but we're going to use this as a rough guide. So we're going to allow our principal group to have a sample size of 120 and a total sample size for the whole trial of 200. So we're going to give 20 to each of the smaller subgroups. So the smaller subgroup sizes are in proportion to the expected size of the subgroups in the population. And one other wrinkle is that the expected control rate on the standard of care is a little bit different across our different groups. In the principal group, the standard of care achieves a 1 point improvement, and then in the smaller groups, one achieves a 0.5 improvement, 2 others a single point improvement, and one has an improvement at 2 points. Some of the other assumptions we need to be able to draw on in order to simulate the trial is how quickly do we accrue subjects. So we're going to assume that there's a sort of a mean accrual rate of 3.3 subjects a week. That's about 14 a month. Once we've reached our sort of average running accrual rate, but it'll take us half a year to ramp up to that speed. For the subjects we do accrue, we expect a sort of a 10% dropout rate, not differentiated by group or arm or particular visit, but just averaged across the population as we observe them. And when we simulate longitudinal data, in addition to our final 26th week visit of a patient, we'll also have visits at roughly every month, so 4 weeks, 8 weeks, 13, 17 and 21 weeks. And we're going to assume that at that first visit, we see about 75% of the final treatment effect. So this is a symptomatic treatment where there's pretty good efficacy at the outset. And really what we're looking at for the 26 weeks is sustained. And we're also going to assume that 80% of the variance endpoint is due to inter-subject variance. And so the observed values of the endpoint of a single patient from week to week has got a lot less variability than the 2 points. So our longitudinal data should be quite informative. And now, what are we going to assume for treatment effect? Well, we're not sure what the treatment effect is going to be. That's why we want to do a clinical trial. And we're going to put in 4 different scenarios. We'll have a null scenario where there's no treatment effect. The effect on the treatment arm is exactly the same as the control arm in all the groups. We're going to have a scenario where there is a treatment effect only in subgroup 1, a scenario where there is treatment effect in subgroups 1, 3, and 5, and then a scenario where there's a treatment effect in all subgroups. And in practice, a larger range of plausible treatment effect scenarios would also be used. And then once we designed a trial with those, we would probably try some simulations with an even larger range of scenarios where some of the other assumptions are varied as a sort of sensitivity analysis to ensure that the design is robust against different dropout rates, different accrual rates, different responses on standard of care. So a little bit of detail on those 4 scenarios we're going to simulate. As I said, we've got this, we've got the groups down here and the 4 different scenarios. In the null case, the response on control is variously 1, 0.5, 1, 1, and 2 across the 5 groups, group 1 being the largest. And in each of the scenarios, if there's a treatment effect in one of the groups, then I'm just giving it a 1 point greater mean treatment effect. So before we get to the results, let's actually see how this all looks when we set it up in FACS. So this is what FACS looks when we start FACS up. And what we want to do is to design a new enrichment design with a continuous endpoint. So we click on that, get FACS into enrichment design with a continuous endpoint mode. And now we start, first of all, entering these aspects of the trial that we want to design before we get to the point where we actually design the statistical elements of the trial. So we have a control arm, a higher response is subject improvement. We're looking for superiority. It's going to be a non-adaptive trial, so we can hide some of the adaptive features. We're not going to use frequentist analysis, and we're not, at this point, going to use longitudinal modeling. We now have to enter the groups we want to simulate. So we've got these 5 groups. We can say that when we allocate to the groups, they've got a cap. Well, the only group we're going to cap is the largest group, because we don't want, just through the randomness of accrual, the group 1 to steal all the oxygen in the room, take all the subjects, and not leave our smaller groups with any subjects. But we're not going to put caps on the smaller groups, just in case the underlying occurrence is not as we thought. And then finally, we're going to place an overall cap on the trial of 200. On the next tab, we're going to specify some rules about how we're going to analyze the data. So we're not going to use the Bayesian posterior probabilities with their clinical significant differences. We're going to make all our decisions based on how well we think a particular population is going to do if we test the treatment in it in phase 3. And so we need to give it the outline properties of this phase 3 trial so we can calculate our probability of success in it. And these would be, we're going to say these will be trials with about 170 subjects per arm, with a one-sided alpha of 0.025. And this would give us roughly 90% power to detect a treatment effect of 0.7. So if we have our treatment effect of 1, then we ought to have a very significantly powered phase 3. Again, to start with, we're not going to do any longitudinal modeling, so we only need to put in the time to the final visit, the 26 weeks. We're not going to simulate any variance, which would allow us to specify different sizes of trial. But we do need to enter our different subject responses. So as I said, we're going to look at 4 different profiles: a null, group 1 only, group 1, 3 and 5, and all groups. In each of these scenarios, the standard deviation is 2. The control response is going to follow the same pattern. And of course, in the null case, the treatment effect will be the same in all groups as the control. In group 1, again, standard deviation of 2, our same pattern of control responses. And in this case, the group 1, the treatment response is going to be 1 point better than control, but for the other groups, it's going to be the same. So groups 1, 3 and 5 now, again, standard deviation of 2, the same pattern of responses on control. And now it's group 1, group 3, and group 5 that have the 1 point improvement, and the other two have a null effect. And then lastly, the all groups, again, standard deviation of 2, the same pattern of response on the control arm. And now every treatment is 1 point better in each of the groups. These checkboxes that I'm ticking here, these are just indicators to the FACS user interface, so that after the simulations are done, when it gets the simulation results back, it can compute how many times in a particular scenario the groups that have got a good treatment effect have actually been successful in the simulations, and it can report some average statistics and proportions of correct group outcome. So on the next tabs, we're just going to give the details of the execution properties. So we've got the accrual profile, where, if you remember, we said that the average recruitment rate was going to be 3.3, and there was going to be a ramp. We'd expect the accrual rate to slowly ramp up over the first 26 weeks. And we also need to put in the relative proportions of the different groups. So if you remember, it was 60% on the first group and then 10% on each of the 4 smaller groups. So 6 to 1 to 1 to 1 to 1. And down there you can see a stacked graph showing the expected accrual into the different groups. We also said there was a suspicion that there would be a dropout of subjects over the trial of about 10%. So we're not doing differential dropout by arm or group or visit. We're just going to simulate an overall probability of dropout of 10%. That completes the setup of the trial we want to simulate. Now we're going to enter the details of the design, how we're going to analyze this. At this point, it's just how we're going to analyze the trial. So we specify 2 models, one how we're going to analyze the control arms, and then how we're going to analyze the treatment arms. Now we're not going to do anything particularly fancy in this example. We're simply going to model each control separately. It's a continuous endpoint, so we shall estimate it using a normal distribution, and we're going to have a Bayesian posterior estimate of the response rate on the control arm. So and we'll have a normal prior for the estimate. So each of these priors will set up the same for each group, that our prior mean expectation is that the response rate is 1, but the standard deviation we'll put in as 2. So the standard deviation of these priors is the same as the standard deviation of the endpoint, so we expect them to have a weight of about 1 observation. So I like to use weakly informative priors like this. Perhaps in this setting with very small groups, these priors should be even less informative, in which case I would use standard deviations that are even larger. Similarly, on the treatment model, we're going to model all the groups separately. And here again we have a model which is simply a normal distribution of the treatment effect, but the treatment effect is estimated as the combination of the effect on the control arm plus some additional treatment effect for the treatment arm. So we're going to put in means of 0 for the additional treatment effect so that corresponds to the null case. And again, we shall put a standard deviation of 2 on each of those priors, and the same for the estimate of the treatment effect across all the groups. And then lastly, we set up a prior for the variance of the endpoint, or the standard deviation, where we give it which we'll be using the conventional inverse gamma distribution. We give it a central weight of 2, which corresponds to the standard deviation of 2 that we're simulating. But we only give it a weight of 1. So again, this prior again is only very weakly informative. It's looking something like that. Now we're going to set up our rules for the allocation. And again, this is going to be very simple. It's a fixed allocation within each group of equal allocation between control and treatment. And I'm going to say 2 to 2 so that it's going to do blocked randomization in blocks of 4. Now lastly, and perhaps slightly more complicatedly than usual, we're going to set up the success and the futility criteria. So we'll start with the lower half of the screen, the success criteria. So if you recalled, we said we're going to use the probability of success in phase 3, and what we're going to look for is either group 1 being successful or the across groups being successful. And we want that ORed together because we either group 1 is successful or the across groups, either one of those is sufficient. So conversely, for futility, again, we're going to use the phase 3 success, but now it's and. The trial will be a failure if both group 1 is a failure and the across groups is a failure. Now, what it remains to be done is to say, well, at what probabilities of success in phase 3 do we say that's good enough to go forward? And at what probabilities do we say, well, that's definitely not good enough to go forward? So I'm going to put in the values I want to use in these simulations now, but then I'll explain where they've come from. So we're going to set for group 1 that we'd go forward to phase 3 if the probability of success in phase 3 was better than 75%. We'd use probability of success in phase 3 for the across groups. We'd go for success if that was better than 0.65. And then for all the smaller groups, we'll judge them to be successful if their probability of success in a phase 3 trial is better than 0.875. As I said, I should be showing you where these numbers have come from, how we derived them. And then similarly, for the futility, we shall declare the group 1 would be futile if its probability of success in phase 3 is less than 0.425. For each of the smaller groups, if their probability of success is less than 0.2. And for the across groups, that its probability of success is less than 0.15. And having entered that, we can now go to our simulations tab and run some simulations. So we want about 1,000 simulations to get a good estimate of how well our trial performs, get a reasonable estimate, not a precise estimate, but good enough at this point in the design of the type 1 error and the power. So Fax is now dividing the simulations across the 4 cores of my laptop. It's performing the simulations in packets of 100, so simulating 100 trials at a time, and it's accumulating those so that for each scenario, eventually I'll have 1,000 simulation results per scenario. So now the simulation results are all in, and we can see that Fax is reporting we have 1,000 simulations for each scenario. Each row is a different scenario. On average, we've got 200 subjects per simulated trial. In fact, it'll be exactly 200 subjects every simulated trial because we've not done any adaptation. There's no early stopping. And we can see that the probability of success in the null case has been about 0.025 for group 1, somewhat less for the smaller groups, and then about 0.045 overall probability of success. So that might be either be group 1 or across groups. And we can look at the overall success rate and futility rate. So you can see we have this overall probability of success in the null case of just below 0.05, and we have a power of about 0.8, 0.85 and 0.95 for the different scenarios where we've got increasing number of groups where we have a treatment effect. And so if you remember, being success relies on either the across groups being a success or group 1 being a success. And then finally we can look at the number of times we've got the correct groups. When group 1 is the successful group, that proportion is quite high. For these later scenarios, the proportion is quite low because we're actually doing a pretty poor job of spotting the little groups when they're successful, because these tests of just in those subgroups is somewhat underpowered. As you can see, it's about the power of detecting these successful small subgroups is only about 20%. So I said I'd explain where those stopping criteria came from, and what I've done is taken the design and I've simulated it 10,000 times. So I've now got a very serious database of simulation results, and I can look, say, on the null, in fact, on the null case, and one of the graphs we have is of the effect of different success criteria. So if I pick my phase 3 probabilities of success, you can now see a line for each of the groups and the across groups, and this is the proportion of simulations that would be successful for different success thresholds. So if I want a roughly 0.025 probability of success in the null case, so in other words I'm controlling my type 1 error at about 0.025, then this is telling me I need a threshold of about 0.65 for success for the across groups, about 0.75 for group 1, and about 0.85 for the smaller groups. Or actually, sorry, 0.875 for the smaller groups, which were the numbers I actually used. On the flip side, if instead we look for the futility stopping, if we look at the situation where we don't want to stop for, determining futility, if we look at the successful scenario, the most successful one where all the groups are successful, so any final determination of futility here is actually type 2 error. It's losing its power, and we can do the same thing. We can look at phase 3 results and the different thresholds that would give us a different level of futility or type 2 error in this positive scenario. And we're going to use 0.5 for the across groups, and then we're going to use 0.45 for group 1, perhaps 0.2 for the smaller groups. So for the individual groups, we're sort of limiting the type 2 error to 0.05. But for the across groups, we limit it to 0.025. And that's where our stopping threshold, our success and futility thresholds came from. As you can see, quite good power and quite good type 1 error control, possibly over control of type 1 error for a phase 2 type trial. And it's tempting to look at whether we couldn't stop the trial earlier if it's clear that it's going to be a success or clear that it's going to be a failure. So we can do that in facts by taking our fixed design. We can save it as, say, now our demo 1 adaptive. We can save our fixed design as an adaptive design, and then with just a few small changes, we can turn it into this adaptive trial. So most of what we've entered, we take some time to enter into facts, is going to remain the same. We've got the same number of groups, we've got the same response profiles we want to simulate. All we need to do is to say, well, now our design is adaptive. Execution, everything else remains the same. But now on the design tab, we get some additional options. We get to specify where the interims occur. So we're going to have an interim every 4 weeks, with our first interim when 70 subjects are complete at their visit. Currently we only have 1 visit. And then on the success futility criteria, as well as the final evaluation criteria that we've already seen, we also specify criteria that can be used at the interims in order to stop early for either futility or success. And again, I'm going to enter some values and we can see what happens, and then I will explain where the values have come from. So for success, again, we want to judge it on whether the treatment effect in that group predicted forward is going to predict a reasonable level of success in the phase 3. And again, we're going to OR conditions together. We're going to enable stopping in all the groups, but we only want to stop the overall study if we're not winning in the across groups. We don't want to just stop the study for success if group 1 is successful, because if we gathered more data, we might actually get to success in the whole population, and we wouldn't want to give that up just because we're successful in group 1. So it's only the success across all the groups that would warrant us stopping early for success. And the threshold for stopping for success for the across groups is 0.9, and for group 1 is 0.95, and for the smaller groups is 0.99. So for futility, again, we're just going to look at this probability of success in phase 3. We're going to add the rules together. Again, we can stop any group for futility. And now what we'll do is stop for the whole trial for futility if group 1 is futile. If group 1 is futile, then that's one of our conditions for success gone. But also, if group 1 is futile, we're not going to be winning across all groups, because group 1 is such a significant part of the overall population. And once again, we have some criteria for this. So we stop for futility for the across groups if the probability of success in phase 3 is dropped to below 0.02, for group 1 if it's less than 0.05, and for the individual groups it's also less than 0.02. Now, we also need to put some caveats on this. We don't want these rules being applied for futility applied too soon. So we're going to say we need at least 40 completing group 1 for it to stop, 20 in any of the smaller groups. And again, we can come here and run simulations. Now, these will take even longer, because one of the main things that drives the simulation time is how long it takes for us to complete the analysis. So previously we got the 4,000 simulations done in about a minute. Now we've got probably 8-10 interims per simulation. So now we've got 8 to 10 times more analyses. So now I might expect this to take closer to 10 minutes. So fortunately, I have some that I completed earlier. So we can again look at the probability of success of the different groups in the different scenarios, the overall success, and futility. So we've got here is now divided into early and late. So we need to add them up, but we've also got some summary columns which give us the overall study futile or overall study success. And you can see that the type 1 error, 0.044, and the power is almost unchanged from the fixed design, which is how we designed it. You'll see in a moment. I've chosen futility criteria in an attempt to avoid having any additional type 1 error, or if I stop early for success, or any additional type 2 error if I stop early for futility. We can see we've got very modest improvements in reductions in the average expected sample size, and we've got similarly very modest reductions in overall time. So let's just again look at how we've used facts to come up with the stopping criteria. And somewhat similarly to the overall success and futility criteria, what I'm going to do is I'm going to take a bunch of simulations, and then I'm going to get facts to present me some graphs of what would be the outcome if at different types of different levels of different thresholds for stopping early for success or futility. So what I've done is I've created an adaptive design with all the interims in, but I've not actually implemented any early stopping. So as you can see, they all run to the end. They all take 200 subjects. But now I can ask facts to analyze that data, to load all these results up, and tell me what would have happened at different levels of success and futility. So I can look, I'm looking at the null case, so I'm concerned about additional type 1 error, so I look at the success criteria. This takes a little while to load. It's loading not just the end results, but now the results of every interim, and it's now looking at what would happen to each of these simulations at different thresholds for success. So I need to tell it I want it to use phase 3, probability of success in phase 3 as its criteria, and we can look at the effect of stopping, in this case, group 1. Just take a little while to reload. Here, facts is showing us a plot of what would happen at different thresholds. You see each line corresponds to a different threshold for stopping early for success, and if that threshold were used for the across groups comparison. Now this is the null scenario. So essentially what I've said is I want a threshold for success which hopefully will stop some of my successful simulations, but won't stop any additional simulations in the null case. So if we look at these lines here, we've got 1, 2, 3, 4, 5 solid lines visible, starting with the dark blue, the very lowest threshold for success, 0.5, 1, 2, 3, 4, 5. So the lowest visible solid green line is if the probability for success is set at 0.9. And as we can see, that green line shows the cumulative number of these simulations that would have stopped early for success. And as you can see, that's barely any at all. So we could use for the across groups a threshold of 0.9, or if we were being super conservative, maybe even a slightly higher threshold of 0.95. And in fact, what I've used is 0.9. Now, using this control here, we can look at different groups and get it to update. And we can repeat the process. And here you can see with a slightly smaller group than the across groups, the probability of stopping for success is slightly inflated. And I'm going to need a more conservative threshold to prevent inflation of type 1 error for my group 1 test. and indeed we used 0.95 instead of 0.9, which we use for the across groups. And then we can repeat this trick for stopping for futility by looking instead at the scenario where all the groups were effective, and I can call up its graphs, just enlarge that, and we can look now at the futility criteria, and on the same basis I can now say, well, what level of threshold for stopping for futility would prevent any of my simulations of a successful treatment making a type 2 error and stopping for futility. And again, it has to reanalyze its 1,000 simulations. Each update takes a little while. Oh, and now it's hidden it. And here it is. And so these are the thresholds for group 1. And you can see, again, we probably want to be about the 5th solid line. So 1, 2, 3, 4, 5, of about 0.05, which is indeed the threshold we set for group 1 for stopping for futility. So that's been set so that we don't expect any loss of power due to our stopping for futility, which is, if you recall, exactly what we saw when we looked at the results. We've got almost exactly the same type 1 error and power. But on the other hand, so although we've preserved type 1 error and power, we haven't actually improved the trial's ability to stop early very much. We were only saving perhaps on average 10 subjects, 20 subjects, which is not a huge improvement, especially for all the additional effort of running interims and interim analyses. So why is this design so poor at stopping early for success? Well, the problem is the data accumulates so slowly. Where's the adapted with early stopping? Here we go. Just look at the futile case. We can look at the distribution of stopping early for futility. So we can see that by waiting for 70 subjects to be complete before we start to look, we've actually already enrolled nearly over 130 subjects, and then we've got a fairly evenly distribution of stopping for futility over time, and indeed some of these have actually completed before they've stopped, even though the total number of subjects is low because other groups have stopped. And a lot of our early stopping has actually fully enrolled, but it's now stopping during the follow-up. And it's this problem of the 26 weeks follow-up that is preventing our early stopping, actually significantly impacting the expected trial size. So what if we could increase the amount of information we had by getting early readouts from the patients and using that to help us make our stopping decisions? So for that, we introduce a longitudinal model. So this is our third and last variant of the design. And in this case, we now additionally check the use longitudinal modeling option. On the visits, instead of just the last visit at week 26, we now specify the visits at the intervening months as well: 4 weeks, 8 weeks, 13 weeks, 17 weeks, and 21. We additionally have to specify how we want to simulate the endpoints we see at those intermediate visits, and we use this hierarchical model to generate the data, and we say, well, we're going to see 3/4, 0.75 of the final fraction, final response at visit 1, and then sort of linearly increasing to the full amount at visit 6. and similarly with the variance, and that the fraction of variance, here's only 0.4. I thought we'd simulated 0.8, I do beg your pardon. So slightly less informative. And then the last thing we do is we need to also include a method of modeling the longitudinal data. We do this in a Bayesian setting, and so the longitudinal model is going to be used to impute the final outcomes for the subjects that are at the interims, the subjects that have been enrolled and have some visit data but are incomplete. And these imputed endpoint values, imputed with some degree of modeling uncertainty, are going to give us some additional information that we can use in our analysis at the interims. We're going to model the two arms separately. We're going to have the same priors across both models. We could have separate models for each group and each arm in each group, but 2 is probably sufficient. We're going to use this time course hierarchical model, which is fairly powerful, and it builds an estimate of the per subject response and the fraction of improvement at each visit using this exponentiated coefficient. And we set up priors for the exponentiated coefficients, the alphas at each visit, and for the amount of variance that's seen overall and the amount of variance that's seen in the per subject component, the deltas. So we put priors on all these parameters, which is a subject for another talk, but these are relatively uninformative. And then we're ready to roll, we're ready to run our simulations again. And at this point, perhaps surprisingly, we find that, these simulations have probably got no early termination. These are used to, yes, we've turned the success criteria off for the early stopping and the futility criteria for early stopping in order to get, again, another database of simulation results, because what we find is that simply enabling a longitudinal model doesn't actually give us, by itself, doesn't give us improved operating characteristics. In order to get the improved operating characteristics, what we have to do is recalibrate the thresholds we're using at these for the early stopping. And what we find is that because of the additional information, we can now make these thresholds more aggressive. So we come up with these improved thresholds, and the result is, again, while retaining the power and still controlling the type 1 error, we now have considerably reduced the number of expected subjects. We've now saved nearly 50 subjects, 25% in the null case, even more in all the treatment works in all groups cases. And even in the case where only one group works, we're still saving 20% of the subjects, and of course a similar saving in time. So lastly, just to summarize those results, we can see for the 3 different designs, the fixed design, the early stopping design, and the early stopping with the longitudinal model design, we can see these different total subject size, expected number of subjects, which are 200 in the fixed case, very slightly reduced with the early stopping, and now much more significantly reduced in the once we introduce the longitudinal model. And similarly, we can see that we've got the same control of type 1 error. It's below 5% in the null case, and we've got very similar power of over 90% when everything works, about 85% when some of the groups work, and about 70% when just group 1 works. So to conclude, we've been able to use FACS to simulate a complex basket trial. We've been able to use the simulation results to understand the properties of the design and to be able to look at how we optimize parameters of the design. We've been able to use features in FACS like interims and early stopping and longitudinal modeling to further optimize the design and to understand and tune those additional properties, again, using the simulations that we can run quite easily in FACS. I do hope that you've enjoyed that demonstration and that it has inspired you to learn more about us, about our FACS software, about trial simulation, and about basket trials. If it has, try taking a look at our website, www.berryconsultants.com, for more information and resources. Thank you very much for watching.